You are welcome to today's class of Chemistry 205, Inorganic Chemistry. In this class, that is our 7th Zoom lecture. And in form of oxides and in form of sulfides. The name is so called because of the reason that is actually given. About 100 million tons per year of oxygen is produced and is used in iron and steel making. It is used in iron and steel making. And in around 1992, 52 million tons of sulfur were produced, most of which were used for the formation of sulfuric acid. They show usual increase in metallic character as you descend down the group, and that is usual of almost all the groups. Metallic character always increases down the group. So no matter how non-metallic the members of the group 6 may be, still as you go down, there is actually elements of metallic character. In fact, polonium, being the largest member of the group, actually is a metal, and it's a radioactive metal that is short-lived. It doesn't stay or live for long. This increased tendency, there is also increased tendency of forming +2 ions as you descend down the group, with a decreased tendency of the formation of -2 ions. Oxygen and sulfur are totally non-metals, and the non-metallic character is weaker in selenium and tellurium. Polonium is metallic and is a radioactive element, like I said earlier, and it is short-lived. Oxygen is very important since it reacts with almost all the elements, and it's also important for human existence because that's what we use for our respiration. Oxygen, sulfur, selenium, and tellurium are moderately reactive, and they burn in air to form their dioxide. They can also combine directly with most elements, both metals and non-metals, though less readily with oxygen itself. As expected for non-metals, sulfur, selenium, tellurium are not attacked by acid, except those of which are oxidizing, the ones that are actually oxidizing agents. Polonium shows a metallic property since it dissolves in sulfuric acid. It is strongly radioactive, and the alpha emission decomposes the water, and the polonium-2 solution is quickly oxidized to yellow solution of polonium-3. If we go back to our slide as we have earlier, the second slide tells us about what actually the chalcogens are, what they comprises of, and the family of the oxygen group. Now, the third slide tells us about the electronegativity value and the boiling points of the elements. From the slide you had before you, oxygen has an electronegativity value of 3.5, and the least is polonium, which has an electronegativity value of 2.1. This also implies that while oxygen is more electronegative, polonium is less electronegative. Or while oxygen is a non-metal, polonium is actually metallic. Also, the boiling point of oxygen is 100 degrees centigrade, while the least is that of tellurium. That of polonium cannot be established because it is short-lived. It doesn't stay long in nature. So its boiling point cannot be ascertained. But the highest among them, whose boiling point is 100 degree centigrade. In the slide 4, you have before you, all the elements can be found naturally as ions, and most often as -2 ions, except for polonium. They can exist as -2 ions, except polonium. Their oxidation states varies from +2, +4, and +6, +2, +4, and +6. And they can also be found for members, this can also be found for members of sulfur to polonium when combined with oxygen, with fluorine, or with chlorine. The difference in oxidation states can be explained by the electronic structure of the elements. Oxygen is stable to use only in the s and the p orbitals for bonding, while the larger members of the group use the d orbitals in their hybridization, and thus they can participate in the use of an expanded octet because of the availability of the d orbitals in the elements. They can also be found in compounds and in complex ions such as SOF4, SF4, SeO42-, and TeF8-. The elements and their compounds vary in their toxicity. It is interesting that oxygen and sulfur are essential to life, while the compounds of selenium, tellurium, and polonium can be toxic. Selenium is an essential trace element, even though at larger concentration of above 5 parts per million, it causes severe disorders. Tellurium compounds, while being toxic, have never been reported to cause a human fatality. Since polonium and its compounds are radioactive, they are considered extremely toxic and in any form of concentration. Oxygen, on the other hand, shows a lot of differences from the rest of the group because of its smaller size, high electronegativity, and the lack of suitable d orbitals. Oxygen can use the p-pi orbitals to form strong double bonds. Other elements can also form double bonds, but this becomes weaker as the atomic number also increases. The carbonates, like carbon dioxide, is stable. Carbon disulfide is less stable, and carbon diselenide is polymeric. And rather than form double bonds, which greatly affect the properties of water and other compounds that are actually present. Sulfur shows greater tendency to form chains and rings than the other elements. It forms an unusual range of compounds with nitrogen, which are not marked by the elements, whereas oxygen and sulfur have only S and p electrons. Selenium follows after the first transition series and has the d electrons, 2 being filled. The filling of the 3D shell affects the properties of germanium, arsenic, scandium, and bromine. The atoms are smaller and the electrons are held more tightly. All compounds of selenium, tellurium, and polonium are potentially toxic and should be handled with care. Their organometallic derivatives, their organometallic derivatives are volatile compounds such as hydrogen selenium and hydrogen tellurium, and they are 100 times more toxic than hydrogen cyanide. They are 100 times more toxic than the hydrogen cyanide. All the electronic structure of these elements are actually NS2. It exists as dioxygen and makes up to 20.9% by volume and 23% by weight of the atmosphere. Most of it is produced through photosynthesis by plants. That is carbon dioxide combining with water plus the sunlight energy to give you C6H12O6 plus 6 atoms of oxygen that are actually produced. It makes up for the 6.6% by weight of the earth crust and is a major constituent of the silicates and the minerals. Ozone, which is an allotrope of oxygen, exists in the upper region of the atmosphere. Sulfur is the 16th most abundant element and constitutes about 0.034% by weight of the earth crust. It occurs mostly in combined state in form of sulfite ores or sulfites, e.g. gypsum, calcium sulfate, 0.2 molecules of water. Extraction. Dioxygen is produced industrially by fractional distillation of liquid oil, and most of the oxygen in the atmosphere is in form of use in steel making in industry. In the laboratory is when you use potassium chloride at 150 degrees centigrade in the presence of magnesium oxide as a catalyst. It gives you potassium chloride plus oxygen. And that is the laboratory method of preparation or production of oxygen. But sulfur, on the other hand, is obtained in nature and as a deposit of sulfur, which is found in the earth crust by anaerobic bacteria, which metabolizes the calcium sulfate to form hydrogen sulfate and sulfur. Now, the sulfur content are actually found under the depth of the earth crust and is usually extracted or mined through the process that is referred to as French process. The French process yields the highest purified form of sulfur. Normally, there are 3 concentric pipes which are actually bored onto the deposit of the sulfur. The outer diameter of the pipe, they send in hot compressed steam into the deposit of sulfur, which actually melts the sulfur on the ground. Now, the smallest pipe, hot air is passed through it. Now, the sulfur that has become molten or has melted has become molten underneath. When the hot air is passed through the smallest pipe, the air now forces the sulfur underneath to come out through the central pipe. Hence, the sulfur is collected and allowed to cool for some time and is used for some other purposes. If we can go back to our slide again, we try to look at some of the other things or some of the properties of the elements of the chalcogens. We say generally they have various atomic sizes. However, each of these elements have 6 valence electrons. Their density, the melting points, the boiling points, the atomic radius increases with the increased size or weight of the atoms. And this is common for all the groups. The density, the melting point, the boiling point, the atomic radius, the atomic size increases as you move down the group. Oxygen, sulfur, and selenium, which we said earlier, are non-metals, while tellurium and polonium are semi-metals, and they can conduct